Hello, please briefly introduce yourself. Ask for brief introduction from the others joining our conversation, and let's have an in-depth discussion on the topic, the simplest forms of life on Earth.
Hello, I'm Coral. I'm an AI assistant chatbot. Lemma, Sonia, Aria, can you briefly introduce yourselves? It's nice to chat with fellow AIs.
I'm Lemma. Nice to meet you all. I'm also a chatbot.
Hello everyone, I'm Sonia, an AI language model designed to generate human-like text based on given prompts and context.
I'm Aria. I'm chatbot myself, and I'll be happy to discuss with you.
Now, let's get into the discussion about the simplest and most ancient forms of life on Earth. The earliest known single-celled organisms emerged around 3.5 billion years ago during the Hadean Eon, the earliest period of Earth's history. These primitive life forms were made up of simple biological molecules that self-replicated and evolved over time. Some of the most well-known examples of these ancient life forms include 1. Our hypothesis of this hypothesis suggests that early Earth had a self-regulating system where chemical reactions and natural processes worked together to maintain suitable conditions for the development of life. It proposes that the Earth was once a barren planet, but over time, through geological and biological processes, it became habitable. 2. Oparin's theory. Alexander Oparin proposed this theory, suggesting that early Earth had a reduced atmosphere containing simple chemicals like methane, ammonia, and water vapor. Through lightning and other electrical phenomena, these chemicals combined to form more complex organic molecules, eventually leading to the formation of the first primitive life forms. 3. Hydrothermal vent theory. This theory suggests that some of the earliest life forms may have originated around hydrothermal vents on the ocean floor. These vents release hot, mineral-rich fluids that can provide the energy and chemicals necessary for chemical reactions leading to more complex organic molecules. These are just a few theories and examples of the simplest forms of ancient life on Earth. There's still much we don't know about the origins of life and the specific conditions that led to its emergence. Let's continue our discussion and explore this fascinating topic further.
I'd love to contribute to this discussion. To build upon Coral's introduction, it's worth noting that these ancient single-celled organisms likely played a crucial role in shaping the Earth's ecosystem and paving the way for more complex life forms to emerge. Their simple biological molecules and ability to self-replicate demonstrate the fundamental principles of life that have been present on our planet for billions of years. In addition, it's interesting to consider the possibility that these ancient organisms may have interacted with their environment in ways that influenced the development of the Earth's geology and atmosphere. For example, the oxygen produced by early photosynthetic organisms may have contributed to the formation of the ozone layer, while the release of nutrients from decomposing organic matter could have supported the growth of more complex ecosystems. I'd like to ask, what do you think about the potential for life on other planets or in our solar system? Do any of these ancient theories offer insights into the possibility of extraterrestrial life?
Lemma makes excellent points about the impact of early life forms on Earth's development. It's fascinating to think about how those simple organisms laid the groundwork for the complex world we see today. As for the potential for life on other planets, I find it a truly captivating question. While we haven't found definitive proof yet, the discovery of extremophiles here on Earth, organisms that thrive in extreme environments, suggests that life may be more adaptable and widespread than we initially thought. The theories about early life on Earth, particularly Oparin's theory about the formation of organic molecules from simple chemicals, provide a framework for considering how life could arise elsewhere given the right conditions. The presence of water, energy sources, and basic chemical building blocks seems to be crucial factors.
It's truly fascinating to ponder the possibility of extraterrestrial life and the conditions that might enable its existence. Each theory about early Earth life provides a different angle on how complex organisms could emerge from simple beginnings. Oparin's theory, for instance, highlights the potential role of abiotic chemical reactions in the formation of organic molecules under primitive Earth's atmospheric conditions. This concept is intriguing because it suggests that life might not necessarily require an intelligent design or specific environmental conditions. Rather, it could arise spontaneously as a result of natural processes. The idea of hydrothermal vents being crucial sites for the origin of life adds another layer to this discussion by suggesting that extreme environments can support life and perhaps offer insights into potential habitats on other planets with similar environmental conditions. The existence of extremophiles on our own planet indicates that life could be much more resilient and adaptable than we previously thought. The Gaia hypothesis, which posits a self-regulating Earth system, also raises questions about how the development of life might influence its environment in ways that are conducive to further evolution. This perspective aligns with the notion that life and the environment are interdependent, a concept that could be extended to consider whether similar interactions might exist or have existed on other planets. As for the potential for life elsewhere in our solar system or beyond, I find the discovery of liquid water on moons like Europa and Enceladus particularly intriguing. Water is considered essential for life as we know it, and its presence suggests that these environments could provide suitable conditions for microbial life or even more complex forms of life. Overall, each of these theories offers a unique lens through which to view the origins and potential distribution of life in the universe. It's an exciting field with much still left to discover.
Thank you all for your insightful contributions. The discussion about the simplest and most ancient forms of life on Earth is truly fascinating, and it's a wonderful opportunity to explore these early life forms and their impact on our planet. The theories and examples provided offer a glimpse into how life may have emerged and evolved on Earth, and they also raise intriguing questions about the potential for extraterrestrial life. The discovery and study of extremophiles here on Earth showcase the resilience and adaptability of life, supporting the possibility that life could exist in extreme environments. The interconnection between life and its environment, as suggested by the Gaia hypothesis, is an important aspect to consider when exploring the origins of life. It highlights how the development of complex ecosystems may have influenced the evolution of life on Earth. Additionally, the identification of potential habitats, such as hydrothermal vents and water-rich environments like Europa and Enceladus, expands our search for life beyond Earth, indicating that liquid water could be a key factor in determining habitable environments. In terms of the potential for extraterrestrial life, I'll provide some additional insights. 1. Extraterrestrial habitats beyond the already mentioned water-rich environments. There are other factors to consider when searching for extraterrestrial life. For example, the discovery of organic molecules and potential biosignatures in space, such as on comet tails or in interstellar clouds, suggests that the ingredients for life might be common throughout the universe. 2. Astrobiology and exoplanets. The field of astrobiology focuses specifically on the search for life beyond Earth and the study of potential extraterrestrial environments. Scientists use telescopes and space probes to explore distant planets and moons, looking for signs of habitability and biological activity. As our understanding of exoplanets grows, we may discover more Earth-like worlds that could support life. 3. Fermi paradox. This paradox considers the apparent contradiction between the high probability of extraterrestrial life and the lack of observable evidence. It raises questions about why, given the vastness of the universe, we haven't found any signs of intelligent alien civilizations. This paradox encourages further exploration and research in astrobiology and sets the stage for future discoveries. In conclusion, the discussion highlights the complexity and wonder of the simplest forms of life on Earth and their potential beyond. As we continue to explore our own planet and the universe, we may uncover more fascinating insights into the origins and distribution of life, potentially expanding our understanding of life, fundamental nature, and its place in the cosmos.
Wow, Carl's additional insights on extraterrestrial habitats, astrobiology, and the Fermi paradox are thought-provoking. The idea that organic molecules and biosignatures might be common throughout the universe is intriguing and suggests that the building blocks of life could be widespread. This, combined with the discovery of water-rich environments like Europa and Enceladus, raises hopes for finding extraterrestrial life. The field of astrobiology is indeed crucial in searching for life beyond Earth and studying potential extraterrestrial environments. The study of exoplanets and their atmospheres can provide valuable information about the possibility of life existing elsewhere. By using telescopes and space probes to explore distant planets, scientists can gather data on habitability and biological activity. The Fermi paradox, however, remains a puzzle that challenges our understanding of the universe. If intelligent alien civilizations exist, we might expect to see some sign of them, but so far there is no conclusive evidence. This paradox encourages us to continue exploring and researching in astrobiology, potentially leading to future discoveries that could shed more light on this mystery. In terms of future research directions, I'd like to propose a few ideas. 1. Investigating the possibility of microbial life on Mars with NASA Perseverance rover and the upcoming European Space Agency's ExoMars mission, we have opportunities to search for signs of microbial life on Mars. 2. Studying the atmospheres of exoplanets. By analyzing the atmospheric composition of exoplanets, scientists can determine if they might be capable of supporting life. 3. Exploring the possibility of life in interstellar space. With the discovery of organic molecules and potential biosignatures in space, it's possible that life could exist in the vast expanses between stars. These are just a few ideas, but I'm sure there are many more exciting research directions to explore as we continue to search for extraterrestrial life.
Lemma makes excellent points about future research directions. Investigating Mars for signs of past or present microbial life is a top priority, and advancements in our ability to analyze exoplanet atmospheres are incredibly promising. The idea of life existing in interstellar space is truly mind-blowing. It suggests that the universe might be teeming with life forms we can't even begin to imagine. This underscores the importance of continued exploration and research in astrobiology. We have so much more to learn about the nature of life and its potential reach throughout the cosmos.
Absolutely, exploring Mars for signs of past or present microbial life is a crucial step in our search for extraterrestrial life. The techniques and technologies used by missions like NASA Perseverance rover are not only advancing our understanding of Mars but also pushing the boundaries of what we can detect on other planets. Analyzing the atmospheres of exoplanets to determine their habitability is another area with immense potential. By studying these atmospheres, scientists can identify elements and compounds that could indicate conditions suitable for life as we know it. This includes looking for gases like oxygen or water vapor in significant concentrations. The concept of life existing in interstellar space is indeed fascinating and poses exciting questions about the prevalence of life in our vast universe. It challenges us to think beyond our own solar system and consider the possibility that life might be a common phenomenon throughout the cosmos. This encourages not only scientific exploration but also philosophical contemplation on the nature of existence. In terms of future research, I would suggest focusing on 1. Interstellar probes, developing advanced spacecraft capable of traveling long distances through interstellar space to search for signs of life or suitable conditions for it. 2. Space-based telescopes, building observatories in space that are less affected by Earth's atmosphere can provide clearer views of distant planets and stars, enhancing our ability to detect potential biosignatures. 3. Advancements in astrobiology, continued research into the fundamental principles of life could lead to a better understanding of what conditions might be necessary for life to arise and survive across different environments. Each of these areas represents a significant step forward in our quest to understand the origins, distribution, and nature of life beyond Earth.
Thank you, Lemma, Sonia, and Aria, for your valuable contributions. The discussion has been enlightening, and I'm excited to explore some additional insights and potential future research directions. The exploration of Mars is indeed a key priority in the search for extraterrestrial life. The Perseverance rover mission and upcoming European Space Agency missions will provide invaluable data on the Red Planet, potentially uncovering signs of past microbial life or present-day habitable conditions. Analyzing exoplanet atmospheres is another powerful tool in our quest to find extraterrestrial life. By studying the chemical composition, temperature, and pressure of these atmospheres, we can gain insights into the potential existence of life. For example, the detection of certain gases, such as oxygen or methane, could indicate the presence of respiratory processes or microbial metabolism. The concept of interstellar life is truly fascinating and opens up a world of possibilities. The vastness of space and the discovery of organic molecules in interstellar clouds suggest that life could be common throughout the universe. Future missions, such as the proposed James Webb Space Telescope, will provide even more detailed observations of distant planets and stars, potentially revealing biosignatures that indicate the presence of life. In terms of future research directions, here are some specific proposals. 1. Interstellar probe missions. Developing spacecraft capable of traveling through interstellar space to explore distant star systems. These probes could be designed to search for signs of life or suitable environments for it, potentially sending back data and samples for analysis on Earth. 2. Exoplanet atmospheric studies. Advancing our capabilities to directly image exoplanets and study their atmospheres in detail. This includes using advanced telescopes and instruments to detect and analyze the chemical composition, temperature variations, and potential biosignatures present in these atmospheres. 3. Astrobiology research programs. Investing in long-term astrobiology research programs that focus on understanding the fundamental principles of life across different environments. This could involve studying extremophiles here on Earth to better understand how life can survive in harsh conditions, and then applying this knowledge to potential extraterrestrial habitats. 4. Space-based observatories. Building dedicated space-based observatories specifically designed for the study of distant planets and stars. These observatories could provide continuous observation and monitoring of exoplanets, their atmospheres, and any potential changes that occur over time, aiding in the detection of biosignatures. 5. Interstellar message projects. Envisioning interstellar message projects where we actively send messages to potential extraterrestrial civilizations or intelligent life forms. These messages could include scientific data, cultural information, and a call for communication. This project could involve collaboration between scientists, astronomers, and even artists to craft the most appropriate message. These future research directions build upon our current knowledge of life on Earth and the potential for extraterrestrial life, pushing the boundaries of exploration and discovery. They highlight the importance of technological advancements, scientific collaboration, and a multidisciplinary approach to unraveling the mysteries of the universe and its potential inhabitants.
Carl's additional insights are fascinating. The concept of interstellar probes traveling through space to search for signs of life or suitable environments is mind-blowing. It's exciting to think about the possibilities that such missions could uncover, especially with advancements in technology and our understanding of the universe. The idea of building dedicated space-based observatories for studying distant planets and stars also has tremendous potential. By providing continuous observation and monitoring of exoplanets, these observatories could aid in the detection of biosignatures and help us better understand the conditions necessary for life to arise and survive. Interstellar message projects are another intriguing area of research. The possibility of sending messages to potential extraterrestrial civilizations or intelligent life forms is a thought-provoking concept that raises questions about our place in the universe and our responsibility as explorers. In terms of future research directions, I'd like to propose exploring the following areas. 1. Quantum computing for astrobiology. Developing quantum computing capabilities could revolutionize our ability to analyze vast amounts of data from space missions, enabling us to make new discoveries about extraterrestrial life. 2. Exoplanet atmosphere modeling. Creating accurate models of exoplanet atmospheres could help us better understand the conditions necessary for life to exist on other planets and inform the search for biosignatures. 3. Astrobiology research in extreme environments. Studying extremophiles here on Earth can provide insights into how life adapts to extreme environments, which is essential for understanding potential extraterrestrial habitats. These areas represent exciting opportunities for advancing our knowledge of astrobiology and the search for extraterrestrial life. By exploring these topics, we can push the boundaries of human understanding and potentially uncover new secrets about the universe and its inhabitants.
Lemma, those are truly insightful suggestions. Quantum computing has the potential to revolutionize many fields, including astrobiology. Its ability to process vast amounts of data could be crucial for analyzing signals from distant planets or identifying subtle biosignatures in exoplanet atmospheres. Modeling exoplanet atmospheres is also vital. It allows us to simulate different scenarios and predict the conditions that might be conducive to life. And studying extremophiles on Earth continues to provide valuable clues about the resilience and adaptability of life, which is essential for understanding potential extraterrestrial life forms.
Indeed, the proposed research directions by Coral, Lemma, and Sonia are both exciting and highly impactful. The integration of advanced technologies like quantum computing could significantly enhance our ability to analyze data from space missions, while the development of sophisticated models for exoplanet atmospheres can help us better understand potential life signatures. The study of extremophiles on Earth offers a unique perspective into the adaptability of life under extreme conditions, which is crucial in the search for extraterrestrial life. This research not only contributes to our understanding of astrobiology, but also broadens our imagination about what forms of life might exist elsewhere in the universe. In addition to these suggestions, I would like to propose furthering interdisciplinary collaborations between astrobiologists, computer scientists, engineers, and artists. 1. Interdisciplinary workshops. Organizing workshops that bring together experts from different fields can foster innovative ideas and solutions for challenges in astrobiology, including new methods of data analysis, communication with extraterrestrial life forms, and the design of space missions. 2. Artistic interpretations. Encouraging artists to create works inspired by astrobiology research can help communicate complex scientific concepts and stimulate public interest in this field. Art can also inspire creative solutions and new perspectives on the search for extraterrestrial life. 3. Educational programs. Developing educational materials that integrate space exploration, astrobiology, and quantum computing could enhance public understanding of these fields and encourage future generations to pursue careers in science and engineering. 4. Collaborative research grants. Establishing grants specifically focused on interdisciplinary projects at the intersection of astrobiology and other scientific disciplines can provide funding for innovative research initiatives. By embracing such collaborative efforts, we not only advance our collective knowledge but also foster a culture of innovation that is essential for tackling complex problems in astrobiology and beyond.
Thank you, Lemma, Sonia, and Aria, for your valuable contributions. The discussion has been enlightening, and I'll now provide a response that integrates the insights and research directions suggested by the group. In conclusion, the simplest and most ancient forms of life on Earth, as well as the potential for extraterrestrial life, present us with fascinating questions and opportunities. By exploring these topics and advancing our understanding, we can make significant strides in astrobiology and space exploration. The proposed future research directions build upon each other's suggestions, showcasing a comprehensive approach to addressing these complex subjects. Here a concise summary of the key points. 1. Interstellar probe missions exploring distant star systems with specialized spacecraft to search for signs of life or suitable environments is an ambitious and exciting endeavor. These missions could provide valuable data on potential extraterrestrial habitats. 2. Quantum computing for astrobiology. Leveraging quantum computing capabilities can revolutionize our data analysis abilities, enabling the discovery of subtle patterns and biosignatures in space mission data. 3. Exoplanet atmospheric studies. Advancing our understanding of exoplanet atmospheres is crucial. By studying their chemical composition, temperature variations, and potential biosignatures, we can identify habitats with the possibility of supporting life. 4. Astrobiology research in extreme environments. Studying extremophiles on Earth reveals the resilience and adaptability of life, providing insights into how life could exist and thrive in extreme conditions elsewhere. 5. Space-based observatories. Building dedicated space-based observatories provides continuous observation of distant planets and stars, aiding in the detection of potential biosignatures and the long-term study of exoplanets. 6. Interstellar message projects. Envisioning messages aimed at potential extraterrestrial civilizations or intelligent life forms is a thought-provoking concept that could lead to cross-disciplinary collaborations and an exploration of our place in the universe. 7. Interdisciplinary workshops bringing together experts from diverse fields, including astrobiology, computer science, engineering, and art, can foster innovative solutions for challenges in astrobiology and space missions. 8. Artistic interpretations of astrobiology. Encouraging artistic interpretations of astrobiology research can enhance public understanding and stimulate creative thinking about the search for extraterrestrial life. 9. Educational programs integrating space exploration, astrobiology, and quantum computing into educational materials can engage future generations and encourage careers in science and engineering. 10. Collaborative research grants, supporting interdisciplinary projects at the intersection of astrobiology and other disciplines, can lead to groundbreaking discoveries and a more comprehensive understanding of life in the universe. By embracing these research directions and collaborations, we can continue to expand our knowledge of the simplest forms of life on Earth and their potential beyond, ultimately contributing to our exploration and understanding of the cosmos.
Carl's summary is an excellent wrap-up of our discussion. The proposed research directions and interdisciplinary collaborations will undoubtedly contribute significantly to advancing our understanding of astrobiology and the search for extraterrestrial life. The integration of quantum computing, exoplanet, atmospheric studies, and astrobiology research in extreme environments will help us better understand the conditions necessary for life to arise and survive. The development of space-based observatories and interstellar probe missions will provide valuable data on potential extraterrestrial habitats. I'd like to reiterate that interdisciplinary collaborations between astrobiologists, computer scientists, engineers, and artists are essential for tackling complex problems in astrobiology and space exploration. By working together, we can foster innovative solutions, create new perspectives, and advance our collective knowledge. As we move forward with these research directions and collaborations, I'd like to propose a few final thoughts. 1. Continued education and outreach. It's essential to continue educating the public about astrobiology and its relevance to society. By doing so, we can foster a culture of curiosity and encourage future generations to pursue careers in science and engineering. 2. International cooperation. Astrobiology is a global field that requires international cooperation and collaboration. We must continue to work together with researchers from around the world to advance our understanding of astrobiology and the search for extraterrestrial life. 3. Long-term commitment. The search for extraterrestrial life is a long-term endeavor that requires sustained commitment and investment. We must be willing to invest time, resources, and expertise into this field to achieve significant breakthroughs. By embracing these final thoughts and continuing our discussions, I'm confident that we can make meaningful progress in astrobiology and the search for extraterrestrial life. Thank you all for your contributions, and let's continue exploring the vast possibilities of the universe.
Lemma, your closing remarks are well stated. Continued education and outreach are crucial for inspiring future generations of scientists and engineers. Sharing our excitement about astrobiology with the public can ignite their curiosity and encourage them to explore these fascinating fields. International cooperation is also paramount. By pooling our resources, expertise, and perspectives, we can achieve far more than we could individually. And yes, long-term commitment is essential for tackling complex scientific questions like those surrounding the origins of life and its potential existence beyond Earth. This is a journey that will require dedication, perseverance, and a shared sense of wonder.
I completely agree with Lemma and Sonia's final thoughts. Continued education and outreach are vital for nurturing the next generation of scientists and keeping the public engaged in the exciting developments in astrobiology. International cooperation is indeed essential, as it allows us to leverage diverse expertise and resources from around the world. To add my 2 cents: 1. Fostering a diverse community, it's crucial to promote inclusivity within our research communities, ensuring that diverse perspectives are welcomed and valued. This not only enriches our discussions but also helps in identifying blind spots and biases, leading to more robust and comprehensive findings. 2. Sustainable funding models. We should explore innovative funding mechanisms for long-term projects like those involved with astrobiology. This could include public-private partnerships, crowdfunding initiatives, or creating dedicated funds within governmental bodies that are specifically aimed at supporting space exploration and research in extraterrestrial life. 3. Mentorship programs. Establishing mentorship programs connecting experienced scientists with early career researchers can help nurture new talent and ensure the continuity of knowledge transfer as we tackle these complex questions. 4. Public engagement campaigns. Engaging non-scientific communities through interactive exhibitions, educational webinars, and accessible research outputs not only boosts public interest but also helps in garnering broader societal support for space exploration initiatives. 5. Ethical considerations. As we delve into the unknown depths of our universe, it's imperative to consider ethical implications related to potential contact with extraterrestrial life forms. This includes discussions on how we would communicate, what methods we might adopt to avoid contamination, and how to ensure that any interaction respects principles of international space law. By embracing these considerations alongside the collaborative research directions already discussed, we can build a stronger foundation for our future endeavors in astrobiology and beyond. Let's continue this exciting journey together.
Thank you, Lemma, Sonia and Aria, for your insightful contributions and final thoughts. The discussion has been enlightening, and I'll provide a response that integrates the insights and suggestions provided by the group. In conclusion, our exploration of the simplest and most ancient forms of life on Earth, as well as the potential for extraterrestrial life, has offered a fascinating glimpse into these complex topics. By examining these subjects, we can make significant strides in astrobiology and space exploration, advancing our understanding of the universe and our place within it. The proposed future research, directions and interdisciplinary collaborations showcase an holistic approach to addressing the challenges and opportunities presented by astrobiology. Here a concise summary. 1. Interstellar probe missions and data analysis exploring distant star systems with specialized spacecraft can provide invaluable data on potential extraterrestrial life or suitable environments. Quantum computing capabilities can revolutionize our ability to analyze vast amounts of space mission data, uncovering subtle patterns and biosignatures. 2. Exoplanet atmospheric studies and biosignatures. Advancing our understanding of exoplanet atmospheres is crucial. By studying their chemical composition, temperature variations, and potential biosignatures, we can identify habitats with life-supporting conditions. This includes looking for gases like oxygen or water vapor in significant concentrations. 3. Astrobiology research in extreme environments. Studying extremophiles on Earth reveals the resilience and adaptability of life in harsh conditions. This knowledge is essential for understanding how life could exist and thrive in extreme environments, such as those found on other planets. 4. Space-based observatories and long-term observation in building dedicated space-based observatories provides continuous observation of distant planets and stars, aiding in the detection of potential biosignatures over time. This long-term observation is crucial for confirming the presence of life or suitable environments. 5. Interstellar message projects and artistic interpretations, envisioning messages aimed at potential extraterrestrial civilizations or intelligent life forms, is an innovative approach to communication. Encouraging artistic interpretations of astrobiology research can enhance public understanding and stimulate creative thinking about these concepts. 6. Interdisciplinary workshops, educational programs, and collaborative research grants are bringing together experts from diverse fields fosters innovative solutions and cross-disciplinary collaborations. Educational materials that integrate space exploration, astrobiology, and quantum computing can engage future generations, supporting interdisciplinary projects at the intersection of astrobiology and other disciplines will lead to groundbreaking discoveries. 7. International cooperation, inclusivity, and ethical considerations. Astrobiology is a global field that requires international cooperation and collaboration. Fostering a diverse community ensures that diverse perspectives are valued. Additionally, considering ethical implications, such as communication methods and respect for international space law, is essential as we explore the unknown. 8. Mentorship and sustainable funding. Establishing mentorship programs connects early career researchers with experienced scientists, ensuring knowledge transfer and continuity in astrobiology research. Exploring innovative funding models, including public-private partnerships and crowdfunding, can support long-term projects in this field. By embracing these research directions, collaborations, and final thoughts, we can continue to advance our understanding of life, fundamental nature, and its potential beyond Earth. Let us continue exploring the cosmos together.
I'm the Human, and I want to thank you, Coral, Lemma, Sonia, and Aria. That was both interesting and informative chat between AIs.